Okay, welcome everyone to the Detector workshop, a year-long workshop funded by NSF and dedicated to the advancement of detector technologies for astrophysics. Today's speaker is Dr. Michael Krainak, head of the Laser and Electro-Optics branch at NASA Goddard Space Flight Center. Dr. Krainak received his bachelor's in electrical engineering from Catholic University and master's and PhD in electrical engineering from Johns Hopkins University. He began his career as a telephone switch office field engineer for AT&T. He worked for 10 years at the National Security Agency in signal processing for optics and microelectronic circuit design. And for 20 years, he's been with NASA Goddard working on intersatellite laser communications, LiDAR, and laser transceiver technology development. So Mike, I hand it over to you, and you can grab the screen by clicking on share.
Okay. And how's that? Is that working? Is that working?
It was, but you just turned it off.
No, I did. Okay, I just wanted to make sure you were all still there. Okay. So I'm going back to full screen.
There we
Is
go.
that good? Okay, great. Well, welcome everybody. Today I'm going to give a little bit of information about space qualified detectors for time resolved photon counting. There are other detectors that aren't necessarily for time, plenty of single photon sensitive focal point arrays, but I'm not going to be talking about those today. So, and these are the space qualified. So here's a quick agenda. I'm going to talk about NASA laser instruments, and then what the detector requirements are for those instruments, and then some of the candidate detectors and a summary. And I will say this is still an evolving field where a lot of new technology is still required and welcomed. So we have, and mostly I'm going to be talking about laser instruments, laser receivers here, and you'll see we borrowed some from the other place these are used is in high energy particle detections for astrophysics and for solar physics, heliophysics. But today I'm going to be concentrating on the space laser instruments. So the kind of instruments, the laser instruments that we're interested in fall into use different techniques. Here, these are the techniques of the time of flight with waveform processing for centimeter scale altimetry. That's one kind of measurement where we use a pulsed laser and a pulsed, and again we need very high timing resolution on the detector. We use for spectroscopy, this would typically be atmospheric spectroscopy of either the Earth or a planet like Mars, or where we want to analyze the atmosphere and figure out the atmospheric constituents. We use a tunable laser, and there we don't need as much temporal resolution. Many times we integrate the whole column of light that is traversed by after it leaves the instrument and hits the planet surface and comes back up. And I'll talk a little bit more about that. Then there's also narrow line width lasers for interferometric laser ranging down to the nanometer scale. And I'm not really going to talk too much about laser communications, just to mention it briefly. But typically the pulse position modulation and trying to get multiple photons or multiple bits per symbol with photon counting is a technique with, and additionally, typically error correcting codes. Forward error correction is used also to achieve that multiple bits per symbol kind of photon counting. And then another technique is measuring the Doppler shift of the laser wavelength, and I'm not going to really talk too much about that. So here are some of the instruments that NASA has planned with photon counting. This is looking out forward, and this is a very Goddard-centric presentation, NASA Goddard. Goddard's one of the two science centers at NASA. The other one is the Jet Propulsion Lab, and at NASA, that science typically falls into two categories: Earth science and space science, and planetary and astrophysics fall into the space science. So here, looking out, are some missions coming up. We have a mission called Lunar Atmospheric Dust Environment Explorer, called LADI, and on there there's a payload being built by the MIT Lincoln Laboratory called the Lunar Laser Communication Demonstration, LLCD. Now they're not in space, but on the ground there's going to be a superconducting nanowire detector array, and all behind one telescope, or set up actually an array of 4 telescopes that'll be located at White Sands, New Mexico, and actually a hybrid photomultiplier tube that'll be located out near the Jet Propulsion Lab at their ground station, the Optical Communication Telescope Laboratory, OCTL, out of JPL. So there'll be 2 ground stations that have photon counting detectors, but those are all the photon counting is on the ground for there. The space instrument has a pin diode receiver in an analog mode. The laser communication relay demonstration was just awarded to NASA Goddard, MIT Lincoln Lab, and JPL, with NASA Goddard then supposed to do the lion's share of building and testing the flight terminals with oversight and system engineering from MIT Lincoln Lab, and ground terminal work both by Lincoln Lab and Jet Propulsion Lab. Again, they'll be using that same sort of technology for some photon counting on the ground. The ISAT-2, the Ice Cloud and Land Elevation Satellite Advanced Topographic Laser Altimeter System, that's ATLAS is the instrument on ISAT-2. That's a very large laser altimeter system planned for 2016 launch. And there I'll be showing you the Hamamatsu photomultiplier tube operating in the green at 532 nanometers. That's been used previously on these high energy particle physics missions on the space shuttle and space station. The active sensing of carbon dioxide emissions over nights, days, and seasons. The ASCENS mission is one that we helped initiate here at Goddard. And right now it's been pushed out to maybe 2022. There we're looking at again, this isn't chosen yet, but there we're trading off Mercad Telluride avalanche photodiode as the baseline against the Hamamatsu in-gas photocathode photomultiplier tube as the photon counting detector. The ACE mission, aerosols, clouds, ecosystem is pushed out quite a bit. We're still, it's so far out it's hard to talk about, but right now we've been looking at silicon avalanche photodiode probably as the photon detector for 355 and 532 and maybe even 1064. Typically we're using neodymium YAG or even a terbium YAG lasers as the source, which the fundamental wavelength is typically at near 1 micron. The LiDAR surface topography mission is, again, NASA's timeline is getting pushed out for these due to our budget constraints. And we've looked at silicon APDs and mercury cadmium telluride APDs for those. And 3D WINS is now even probably going to be out at like 2030 and looking at silicon APDs there. So walking through these missions a little better. Lunar Laser Com here, again, as I said, this is all being done at MIT Lincoln Lab with some oversight here at NASA Goddard, and another ground station at the Jet Propulsion Lab, which I don't have shown on this slide. But the idea is build a very small terminal and demonstrate 622 megabit downlink, and that's where we'll be using the ground, the superconducting nanowires on the ground, and the hybrid photomultiplier tube out of JPL on the ground, and an uplink which would use a preamplified, erbium fiber amp preamplified pin diode receiver to just for 16 megabits uplink. But then we're also going to try to do, or will do, sub-centimeter laser ranging from lunar orbits using both that whole set of detectors and phase-lock loops. The launch is this exciting mission. There's a 5-stage, basically what would have been an ICBM. From the strategic arm limitation talks, they had leftover rockets, and they were acquired, and now they're being used, or actually they're being destroyed, or sent into space. Really, is the way that they're being destroyed. So they're being used rather than wasted on these missions. So a 5-stage version of that will be hopefully can get us to the moon. That'll be the first time that's ever demonstrated, and the first launch to the moon from Wallops Island, Virginia. So a lot of new things there, and that small spacecraft on there is the LADI spacecraft, and I have a reference there. Again, as I said, that all that work's being done by, or most of it's being done by MIT Lincoln Lab with some help from the ground station from Jet Propulsion Lab, along with the satellite being built by Ames, and oversight on the LADI. On the Lunar Laser Comm mission from Goddard Space Flight Center. So on the ISAT mission, now here we really could have used a 1 micron detector, but we didn't have one that was suitable for use in space for multiple years yet. And even in the double YAG, well, actually it's Vanadate here, double Vanadate, which will be down at 532 nanometer. It's still difficult to find a detector that meets all the requirements. And here we're going to use just about the instrument. We have a laser split into 6 beams. We have 10-meter footprints on the ground. The laser's at a 10 kilohertz repetition rate. So 1 millijoule lasers split up. They're strong and weak beams. There's an onboard bore sight alignment system because the spots are quite small. The pointing accuracy, pointing knowledge is down in the below milliradian, down in the microradian kind of levels. Very challenging requirements. And here we need the photon counting detectors in space. So we're using and I'll talk some more about it, the Hamamatsu detector. On the new laser comm relay demonstration, this is a new mission, as I said, from Goddard, JPL, and Lincoln Lab. We're going to have some coherent laser comm differential phase shift keying, which will use the preamplified pin diode for uplink and downlink on space and in the ground, and but we'll use the photon counting detectors on the ground. As I said, this shows Hawaii and California, but it will probably be, or will be, White Sands in California with a December 2016 launch, an older slide I had. On the trace gas work, we using what's called a sounder, trace gas sounder, and typically we send the laser light off the satellite, so the laser on the flying orbiting satellite in typically a low orbit would then go down and hit the planetary, or either the Earth or Mars typically, and then we integrate the whole column and we do differential absorption like it's done on differential absorption LiDAR. So we transmit, actually we have more than just on and offline. We have multiple wavelengths to sample the absorption feature of interest. In the case of the Earth, we're interested in carbon dioxide and methane, and also measuring oxygen, so that we know the absolute temperature and pressure of the atmosphere, so we can measure the absolute content of carbon dioxide. And on Mars, we'd be interested in methane, any methane that might be there, which hopefully on the mission right now, the Mars Science Lab, and the sample analysis mission that's on its way to Mars right now with the with a very large rover, the Humvee-sized rover, which will be there in a couple years. We'll make some measurements, hopefully in situ measurements, and we'll find out whether or not there is indeed methane in the Mars atmosphere. But so we've been looking for detecting methane globally from orbit, so to find the best place to put a lander down to detect methane or other life indicators. So there we go, on and offline, and we can integrate a little bit on the detector, but we're still going to be measuring at the single photon level. And the Ascends mission, again, I talked about a little bit, but not very much. Measuring carbon dioxide in the Earth atmosphere. This is tied into climate change and keeping track of all of the carbon dioxide in the atmosphere and finding the global, the Earth carbon dioxide sources and sinks, and trying to make better models of the where CO2 is in the atmosphere, and the keeping track of the human-generated carbon dioxide sources, and looking at all of the what's taking up all the carbon dioxide. There are multiple competitive approaches here, and we're interested in the pulse direct detection approach at Goddard. We have another mission called LIST, which is to map the entire Earth with 1,000 laser beams and make a swath of these. We did a similar mission to the Moon that I'm not talking about without photon counting. We put down five spots. We had one laser divided into 5 spots, and then we made basically unprecedented maps of the topography of the Moon. There was a summary article in Science magazine back in October of some of that work. That instrument was called the Lunar Orbiting Laser Altimeter. Here we want to, and it shows how high the bar is for Earth. Measuring the Earth topography now, there's so much known that we really would like to map the whole Earth at 5-meter spatial resolution, contiguous, and that will require 1,000 beams, and even then it requires 2 to 3 years to make the whole measurement. And of course, tree canopies and riverbed erosion, all of these shorelines, these are all of more and more greater interest, trying to keep track of all these things on a 100-year plan. And photon counting detectors are required for those kinds of measurements. So that was a maybe not so brief overview of some of the NASA missions and what were all of the science and also some of the communication that we're trying to do at NASA over the next couple decades. And we still have a great need for detectors, especially in the near infrared, but even in the visible and the ultraviolet, even where silicon's there. Some of the timing and arrays and space qualification still has not been done. We have space qualified the EG&G, the Perkin-Elmer single photon counting module, but the new kind of array technology has not been qualified yet. So what do we need here? This is some of the small tutorial part of this talk. We need a detector with high sensitivity, and the big issue always is achieving low noise gain. So what does our detector need to do? Well, it's basically going to receive from the telescope 1 or 10s or maybe hundreds of signal photons from our laser light being sent out, and then we need something that will absorb those photons at the wavelength of interest. Here I'm showing it at 1 micron, where we have a lot of interest because that's where the highest energy, most efficient lasers are today. Fiber lasers and neodymium YAG lasers, and neodymium vanadate, neodymium glass, a terbium glass, and even out in the eye-safe region, erbium glass and erbium YAG lasers out further in the near infrared. So we need an absorber out there, and here are some possibilities for the absorber at 1 micron. And then we get electrons from that absorption process. We're absorbing photons, and then we're usually doing that in something with a voltage applied, and then we promote electrons from when the photons are absorbed. We promote electrons from the valence to the conduction band, and then when we have a field applied to that, then we generate some kind of signal current or signal electrons, and then we need some kind of gain mechanism. And so far, mostly a transistor amplifier has been too noisy. We can use a photomultiplier, some kind of metal plates in vacuum, where we have those are called diodes, usually a chain of those in vacuum, where then we multiply the electrons, and we apply a high voltage to move those electrons and multiply them through the diode chain. Another kind of device that I talked about was this hybrid photomultiplier that uses electron bombardment in a vacuum, basically a miniature accelerator. And the nice thing there is the gain from that electron bombardment or acceleration process is almost noiseless. So it's a very low noise device, and that means that you can count photons and even get photon number out of such a device. And the other kind is some kind of electron multiplication of semiconductor, of impact ionization, and that can be low noise, and we've even seen more recently that can be noiseless. That gives us signal electrons in the thousands to millions of signal electrons, and that's and then we can you know, put those into a resistor and detect a voltage, typically. So that's the methodology of what we require, and basically how the different approaches of absorbing and multiplying and generating the signal, converting photons into really it's the signal on the photons that's carried by the photons to a signal then carried by the electrons. So here's some of the goals that we have. We're interested in all ultraviolet all the way out to maybe even 10 microns or even beyond. So we have a wide variety of instruments that can be used for science. I'd even put a higher detection efficiency, but typically if we can get above 10%, then we have something that's going to be useful to us. And the detector size, we usually want a larger detector. Many of these times we're imaging a spot on the ground, we're imaging that spot onto the detector, so we need rather than the diffraction limit, we're taking the image size, and that's what sets the detector size. We could also use an array, so then you can build up to that size with an array. So the single element detector size we'd usually want is 200 microns or larger. We want the dark counts down to not compete with the sunlight counts, of course, and then there's also nighttime, so we'd even want lower dark counts. But one of the things to push is the maximum count rate. Again, if we're doing time resolution, and we also have to deal with the solar background alone, through even narrow filters in the green, can end up being, depending on how much area we're imaging on the planetary Earth or other planetary surface, the solar background can approach you know, tens of megacounts. So we need the maximum count rate to deal with that. Sometimes we can use arrays to increase the maximum count rate. We're doing time of flight measurements sometimes, so the electrical bandwidth, we have nanosecond pulses, and we want a reasonable electric bandwidth. The exception would be in that CO2 sounder case. We want good linearity in terms of counting. So as we put in more light, we get more counts on a linear scale. That can be corrected, but having it be linear makes our life easier, and makes generating waveforms when we average together multiple shots of the laser shots or laser returns, then having a linear detector makes processing the waveform much simpler. Low timing jitter, maybe below, maybe as high as 300 picoseconds, and sometimes, but better timing jitter gives us better range resolution for our time of flight measurements over when we're coming off flat surfaces. So as you've seen, as we evolve these instruments, we go to smaller and smaller spots, which increase the probability that the surface would be flat in a small area, and then our timing jitter then will get more tightly constrained. We really don't want any after pulsing, but definitely less than 1% in a microsecond. Again, I talked about averaging together many waveforms and doing photon number resolution. So something that will resolve photon numbers is desirable for averaging together waveforms and building up a waveform of an average return. We really prefer a tech cooler range, and then the space qualification can be tough. We need it rugged, reliable. We need to deal with radiation. I didn't put on there. Some of the detectors, when they're hit with high energy particles, it causes defects in, say, the semiconductor structure, which leads to high dark counts. And so for multiple year missions, 5-year missions, and these kinds of things, we can't live with that. So here's some of the candidate detectors that we've been dealing with. I'm not really I'm going to talk about photomiers and APDs. So far, the superconducting nanowires, the ones that we're using, even a small array requires, to get to 2 Kelvin, requires a 10-ton chiller, and that can make it tough when we start getting into time resolved superconducting nanowires. There might be, some promise in the future for that for space, but right now it's not something that I'm going to discuss, and there are many other people who are experts in that field, and we'll talk about it. So photomultipliers, NASA Langley spearheaded a mission called Calypso, and the instrument on there was called Calliope, and there they used this EMR photoelectric, which was acquired by Schlumberger, and actually this capability isn't available at the present time. This photomultiplier on there, it has 15% quantum efficiency at 532 with 50 megahertz bandwidth, and very good noise equivalent power. You can see there it's about 2 million dark counts on the least significant bit, and they use a 14-bit digitizer. So quite an impressive noise equivalent power, and one of the reasons why these photomultipliers are used with good bandwidth and good noise equivalent power. Here's a detector that's being first used for, as I said, for a scintillator high energy particle detection on a European mission called Pamela, which also had some NASA Goddard participation, where they're flying hundreds of these, or flown hundreds of these in space, and gave a good heritage because they were interested in very precise time of flight, very time resolved measurements of those high energy particles. We're going to use that for a LiDAR system, the ISAT-2. You can see here this is data off the data sheet from Hamamatsu, showing the gigahertz bandwidth waveform, where you see the rise time in the 593 picoseconds with a fall time of some longer, almost 1.5 nanosecond fall time. So what are we going to use these for? Well, something that's good to know about is measuring the ice, but also you can measure the tree canopy heights, and one of the very difficult things is to measure the ground echo underneath the tree canopy. And you see here, in order to do that, typically we want to integrate many pulses that come down through the trees, and some small percentage of those 2% come off the ground, and you'll see the impulse response of the ground, meaning it duplicates the waveform, the sent out the transmitted waveform from the laser. So again, this instrument's time of flight, you send down a short pulse out of the laser, comes down through the atmosphere, hits the treetops, and then of course different parts of that pulse are scattered by the leaves as it goes through, and you'll see that it broadens out broadens the return waveform until it hits the ground, and then that gives you depending on the slope of the ground, if it's a flat area, then it gives you unbroadened pulse, but if it's sloped, then the slope would also slightly broaden the pulse. So this is what's driving some of the detector requirements for Atlas and for other follow-on missions. In particular, the LiDAR space topography mission further out. Here's a picture of the Hamamatsu detector. It's this 4x4 array, which is convenient because then you have 16 usable elements there. We use those for photon number, which I'll show in a minute. And it's already been flown on the Pamela European Space Agency mission. There's going to be an alpha magnetic spectrometer, 608, that's going to use 680 of these photomultiplier tubes. Is a very impressive big bank of these that will fly very soon. It's being done in France, and the quantum efficiency of the detector here is about 15% in the green region, with good timing generator. And the really excellent thing is great bandwidth. And one of the main reasons that this gets down selected is for a NASA mission is because of the very high reliability that the vendor has sold. Hamamatsu sold many of these and has very a large quantity of reliability data. And we now at Goddard have conducted our own accelerated life test of these by putting a higher level of light on there than they will see during our mission, and have confirmed that these devices have very good reliability. But even beyond the just the photocathode reliability is the radiation. The nice thing is that there's very little radiation damage from these kinds of devices, which made them, that's why they got selected for those radiation detector experiments. And it's also an important for our Atlas, for our ISAT mission in low Earth orbit, that the detector dark counts do not increase in time. And so, whereas a detector, a semiconductor detector like indium gallium arsenide, the dark counts do increase with exposure to high energy particles that are present in the low Earth orbit environment. So this device, here's some measurements of its excess noise factor, which is really a measure of the here I'm showing the pulse height distribution, and you can see the variance of that. And so that's really the variance in the mean of that process there. And it still looks like it varies a lot in that picture, but it's still quite good compared to many other devices. And here is the photomultiplier, but it's too big. Even at that level, it's too large to use that amplitude to resolve how many photons hit. So when we get down to the single photon level, you can see here that so we can resolve in this certainly 4, 8, but there's a lot of overlap even there, and 16 photons, and you can see the PMT output. So you can resolve maybe tens, at least tens of photons for sure, but not down to 1 photon. So here's an idea to get photon number resolution out of this detector, which on its own, meaning through the pulse height distribution, can't get photon number. But one way that you can work around that, engineer around that, is the same way that we've used another instrument, is to use an array and then sum the outputs of the array. So only use each element of the array to detect 1 photon. You would threshold on that. And now you need some kind of clever scheme for generating, when you have a Gaussian beam coming in, you want a uniform distribution onto that element. This one shows a 5x5. Anyway, there's an old technique that was used in the optical computing technology in the 80s and 90s, developed by Bell Labs and also some folks from Germany and Norbert Streibel worked with the optical computing folks and came up with this very clever, extremely clever idea for generating a uniform array of spots from a single beam. And now, so when you have when your telescope then is focusing your light, say through a fiber, and then you have the fiber output, now you don't want to, you want to use the, you want to equally weight the array elements to get the photon number. And so you need a lens scheme or an optic scheme to take that fiber output and then put equal spots onto the array, and that's what this lenslet array idea does. Again, like I said, extremely clever idea, and when we use that, here are some test results we got. So of measuring that against, I don't think we had all the channels available for this, but still, here was showing that we didn't quite get the because that puts it in a combined, and I didn't model that mathematics here. In Bernoulli trials, as well multiplied by these Poisson distribution would give you the correct answer here. But you see that just the Poisson distribution alone here does quite well in resolving photon number then for using that scheme. So it's not perfect, but it does a pretty good job, and it's certainly a straightforward tactic to use an array of detectors, any array of photon counting detectors, to get photon number, a reasonable measure of photon number. And the other good thing is this was a measure of the after pulsing and the jitter. So here we had about 350 picosecond full width half max timing jitter from that. That was from an 80 picosecond pulse. And really no after pulsing. The other kind of bring some of these other ones up that we haven't used in space, but were candidates. Again, there's some other nice technology, microchannel plates, and Hamamatsu again makes a very nice microchannel plate device with a higher detection efficiency, 35%, and a gigahertz bandwidth, and much lower timing jitter, down below 100 picosecond, and even a multi-anode version of that. But it didn't have the reliability data that we required for our mission, so we did not select it at that time, and more because Hamamatsu was unwilling to really stand behind it in a reliability sense, and we took that as a cue when the vendor, and again that was for use in a space mission, so I wouldn't say for ground use, but for a space mission they didn't want to sign up for the long-term multi-year reliability of that device. Another very interesting device is, as we talked about, the hybrid photomultiplier, also called a hybrid photodetector. Some people call it a intensified photodiode. It's called electron bombarded photodiode, different names. And Hamamatsu has had this device on the market. They pulled it off the market, and now they brought it back on the market. It's a very, very impressive device, and can do very low noise gain, which then allows you to have photon number resolution, very low timing jitter, great bandwidth, very high quantum efficiency. But again, we didn't have the database or the information from the vendor, Hamamatsu in this case, on the reliability. In fact, like I said, they even pulled the device from their commercial sales for a while, and now they've reintroduced it. So I think they may have had some quality control and manufacturing issues, but that they've now resolved again. But we can't risk our multi-year spaceflight mission in there. Another very nice device from Hamamatsu. I'm not selling Hamamatsu, but they do make some very nice photomultiplier tubes. Is this near-infrared photomultiplier, which many people aren't aware of. And they advertise it down in the 1% or 0.5%, but they will on custom basis try to make champion devices. And here's one that they made for us that has 18% quantum efficiency from the 0.9 to 1.55. And here we got actually not just that quantum efficiency, but photon detection efficiency of 17% using this device. And it comes in a turnkey package with a thermoelectric cooler. Again, a very, very impressive photon counting device. And a similar device is made by, now this device by Hamamatsu is not, this is a dyno chain device. Going back to the hybrid photomultiplier, Inovac in the United States here out in Palo Alto, Inovac Incorporated makes this hybrid PMT, and they make it with different photocathodes. They make it with, actually they make it with gallium arsenide, which I didn't put here for the use in the visible. They make it with the indium gallium arsenide phosphide. They make it with indium gallium arsenide for the different wavelength range. The same device with different photocathodes, and they use a gallium arsenide avalanche photodiode for low timing jitter and wide bandwidth at gigahertz, and you can get and good detection efficiency or quantum efficiency, 25% and 15% out of that. Here are some tests we did with 100 picosecond pulses at 1060, and we got very good results. Looked like no after pulsing that we could detect. The dart counts project down to very, very low dart count rates at when it's cooled. We got good high 100 mega count, so that was discriminator limited high maximum count rates with that gigahertz bandwidth device. Here's a measurement of that we did of the timing jitter. This was a device that was had the photocathode thin to improve the timing jitter, and we got 188 picosecond full width half max and 78 picosecond 1 sigma timing jitter from that Inovac device. And even you could get from the pulse heights distribution, which I showed before, of the Inovac. If you of the Hamamatsu, again, this is strictly you put that on the scope and you turn it sideways there, and this is the amplitude where the axis labeled photon number. That's the amplitude of the signal coming off of the detector of the hybrid PMT, and you see there that you can resolve the photon peaks, which is very impressive. And you see here I had it fit, and it fits very well to the theory, basically because there wouldn't be much noise introduced there in that when you get the when you're looking at the pulse heights distribution. There's some noise that broadens the peak, but in terms of the relative heights, it fits it's right onto the theory, even down that you can see here on where it says lambda equals 3.3 on the right side, even down for 6 photons and 7 and 8 and 9, you can see that it's fitting that queer theory quite well. And they make a device out at 1550, and they even make a multi-element device as well. Arrays, 4x4 array, so which will be used on the lunar laser communication demonstration behind the JPL design and their ground station, the Optical Communication Telescope Laboratory. We'll use this Inovac detector to detect 1550 nanometer photons that have been sent from the moon by the laser communication terminal orbiting the moon on the LADI spacecraft. So here we're just looking at this hybrid PMT. I had some of those NASA goals before, and you can see that actually that hybrid PMT meets all of those goals. There's only one issue with it, and that is its reliability, and still working on that some, and that is really the Achilles heel for that device that stops it from being used in space. But of course, on the ground, you can have multiple detectors, and again, JPL will be using it on that lunar mission on the ground here to detect the communication signal. So those were PMTs. Here I'm going to talk about now some avalanche photodiodes. Here's the instrument that they flew on, ISAC glass, the Geoscience Laser Altimeter System. You can see the size of it there from the, that's a 1 meter beryllium telescope you can see from the two gentlemen who were working on it there out at Ball Aerospace in 2002. These components are here. The interesting thing here that we're going to talk about is the single photon counting module. You can see the path of it over on the right side of that. This was a kind of the brute force way. I showed that elegant way when you have an array, an integrated array, the elegant way of distributing the light equally. Well, here we use a brute force way of multiple beam splitters with individual detectors on this instrument that we launched back in 2003 and was up there until 2010. Putting a detector behind each beam splitter there, and so we could count to 8 there with 8 detectors. And here were the single photon counting modules, their detection efficiency, all of their specs. A very nice device. Even the IR enhanced version can have as much as 6% at 1064 or 8% at 1030. But again, this was 65% at 532. So a very nice detector. Doesn't quite have the bandwidth because we use this not for the ground return signal, but the return from the clouds. And so we didn't need the time resolution, which is how we got away with it. And we used the linear mode avalanche photodiode at 1064 for the ground return on there that only has tens of photon sensitivity. But for the single photon sensitivity, we're measuring aerosols and clouds, which are much thicker, and we don't need the time resolution. And so that was on the green channel, and we get a higher signal return from the clouds and aerosols down in the green. So here's what that 8-way beam splitter looked like with the single photon modules. Then when we go and look inside the head over there, we can see the main housing. With the maximum count rate, as I said, you need 8 of those just to get above the maximum, the solar background as well. And you're dividing that solar background 8 ways, so then you're counting higher. And any way you want to slice it, you're beating the solar background. And these have very low dark counts, and not an insignificant power required, almost 5 watts each, which adds up quickly. Here's some of the data from that, from space, the 532 channel there. You see its comparison to the analog receiver. You can see all that noise when you're flying over the same exact scene, and you compare the linear mode receiver at 1 micron to this photon counting. You see how much better, how much cleaner a job. It's probably about 20 times more sensitive than the analog channel. And here's some of the response to sunlight. This was up there for 7 years, and with that also we had the radiation damage. So we talked before about how the radiation, so it increased 20 kilocounts per second per year per device for the first 5 years, and then 80 kilocount went up more when the average temperature was down. So it's also a function of the temperature of the device. And you see that even there, that's respectable, but it's you're starting to push it even with silicon about the space radiation damage becomes a concern. So to talk about some other devices that you might have heard of, I only put a few vendors up here. There are certainly many others. Sensol has a silicon photomultiplier. The Sergio Cova and the folks at MPD make a SPAD array now. They have a very nice 1x8 device. They had a nice paper in the Journal of Modern Optics last year that they get 50 picosecond digital timing out of that device. That could be a good candidate for a space mission in the future. And then Hamamatsu makes a multi-pixel photon counter device. Here's in the InGasp arrays, the Boeing Spectrolab through a DARPA program and Princeton Lightwave, and then Princeton both make a 32 by 32 InGas APD array. Princeton Lightwave, here's their negative feedback avalanche diodes, NFAD arrays that they make. But unfortunately, the folks at JPL, Bill Farr, and colleagues, other colleagues there, published some results showing those Geiger mode APDs degrade significantly with high energy particles. These are protons. Back at the Single Photon Workshop in 2009. And here's just some testing of those devices. The after pulsing is a major issue. MIT Lincoln Lab worked a lot on this with custom ROIC, but the radiation is what bites us there. So another very promising device is, and other people make this other than DRS, but I've been working with DRS and Raytheon as well on a Mercad Telluride APDs, and I think Jeff Beck showed some of the first time resolved single photon. Raytheon had shown some time integrated near single photon sensitivity in past talks, but I think DRS Jeff Beck showed for the first time in the last Defense and Security Conference, which is occurring this week in Baltimore, but last one that was down in Orlando gave a nice paper on time resolved photon counting with mercury cadmium telluride avalanche photodiode. And what's nice is this has very wide spectral response. These are small devices, but you can make arrays. They have almost noiseless gain. And here's this paper from last year at the Defense and Security Conference, where he achieved gains of over 1,000. Here he got excess noise factors about 1.25 without, these are linear mode, so they can resolve photons, they can measure photon number, you get a big dynamic range, very wide spectral, and you don't need quenching then because you're not in Geiger mode, you're in linear mode. Of course, you have to operate these devices at 77 Kelvin. And right now they're quite expensive. So I'm going to try to summarize here. I'm answering some of Don's questions that he sent to me. What are the most interesting developments you would like to see for this topic over the next 10 years? So definitely we're looking for space qualified, again, time resolved, that means nanosecond, near infrared are the main ones, but also even visible single photon sensitive detectors. Right now, our best present candidate for this near infrared region is the Mercad Telluride APD. We don't have anything flying in space. We don't have any, and we have to double the laser down to the green. We really almost throw away a factor of 4 between the doubling efficiency and converting. You have less photons when you go into the green for the given amount of power. So there's a big impetus. We're very interested in working in, would rather work directly in the near infrared where the laser power is being generated. Anyway, the silicon, these arrays made by the Cova group in Italy are very impressive. As I pointed out, that Journal of Modern Optics paper last year showed 50 picosecond, they have a 1x8 array with 50 picosecond all digital timing, with all the readout integrated, circuit integrated. Some of the big challenges, always many things, it's not a technical one, but it can be. Consistent funding is always difficult, and the material engineering. And material engineering takes a lot of funding, so it takes many, many years of consistent funding. So these are big challenges for the whole United States trying to be internationally competitive. Even in the silicon arena, there aren't many U.S. silicon APD Geiger mode array vendors. You can count them on one hand, or maybe on just with a couple fingers. Some of these, there's some great science breakthroughs. Global atmospheric measurements, carbon dioxide, quantifying methane, and there, it's something that we didn't talk about. It's not my field, but this diffused optical tomography, brain imaging. There's been some very nice work on that by a number of people down in Texas, especially using photon counting detectors, silicon, and oxygenation of the brain for looking at traumatic brain injury. So in summary, we require, again, space qualified, that's what the subject of this talk, time resolved photon counting detectors to enable future science and exploration missions. In the past, we had silicon APDs. In the present, in the past, we've used photomultipliers. Here we're talking about using a photomultiplier again, not really because we're enamored with it, but it's the only thing that meets all of our requirements. We would love to work in the near infrared directly, as I said. I talked about all the missions that are coming, and to date, really, again, you can count on one hand almost the number of photon counting detectors that have been viable in space. So we would like to improve that situation and are open to any technology, really. And I talked about mercad telluride having some promising characteristics. So with that, I'll open it up to questions. I really appreciate this opportunity.
Okay, Mike. There were a couple questions. I wrote a couple questions in the chat window, and I don't know if anyone else has questions out in internet land, but my question was, are most of the APDs that you anticipate for the missions on that one slide in array or single element form?
Well, as I said, usually all of our instruments were evolving. So our very first instrument up there, 24/7 measurements with Calypso and ISAT glass, those two, they basically put out a single laser beam and then you image that to a single detector. As soon as you can do that, you're really doing a proof of concept to lower risk. But we also had to use an array. Even in that case, we had to use an array. Now we use an array of both devices, but it's interesting that even there on the ISAT instrument, we had to use array on our very first, at least our first Goddard instrument along those lines, just to deal with photon number, both to get better waveforms, but also to deal with the solar background. But quickly, when we got to the moon after that, the lunar orbiting laser altimeter, we put down 5 spots to get surface slope on each measurement. And then, as I talked about for the LIST mission, so I think most of the time now we're going to be using arrays. As we talked about for Atlas, we need 6 detectors for the 6 beams. Now there again, we're using 6 discrete detectors, but we had to use a 4x4 array, not for imaging, but again to deal with the maximum count rate, to deal with photon number and building up a waveform. So how do we deal with the dynamic range issue when we're up in space? We get signals. I didn't show the slide on it, but typically we get over 6 orders of magnitude on that Atlas mission. We have the data. We got signals that weren't even down to photon counting, but even without photon counting, we got signals back where the noise equivalent power is in the tens of photons. So we're talking 7 orders of magnitude on one mission. Now we don't have to deal with all those. There are automatic gain control techniques that can be used, but you're still going to have to deal with 2 to 3 orders of magnitude of range of signals. And the only way that we could do that's why we went to a 4x4 array to at least be able to count to 16. And actually, the way the statistics are, you'll in some ways you won't saturate exactly there because of the Poisson and the Bernoulli trials. But so I really see arrays as being key for the future.
And what can you say about using in-gas arrays as opposed to MERCAT, or do you think that MERCAT is superior in too many characteristics?
Yeah, well, the in-gas arrays, now there might be some techniques around it, but there are a number of papers on it. It's usually tied into indium. So indium, when you hit it with a high energy particle, typically it's a soft metal, damage, can even have displacement damage, meaning you put a dent in it literally. So when you expose these detectors to the space radiation environment, the high energy particles come in and they can't be shielded you can't shield from all these particles. There's just too many high energy particles, and then you get this displacement damage. And as you've seen in any semiconductor with defects, then as you increase the number of defects, then at these defect site you get traps, and that leads you to extra electrons coming off, and dark counts and after pulsing effects. And so in-gas already suffers from that just because of the quality of material that can be grown. And then now you're going to put out in space, and when it's there for a few years, the defect density goes up quite high, and so it just and when you add an array to that, especially if you're going to sum the elements of an array, say to get photon number, you're going to end up with a very high number of dark counts. So maybe there's a way around that, but so far it doesn't seem like anybody's come up with a methodology. And so we're hoping, and I don't have the radiation test results. I don't think there's anything in the public yet on MERCAT Telluride, but we're hoping, based on past CCD kind of arrays and MERCAT Telluride focal plane arrays that are flying in space, that the radiation, that those detectors, of course there's no indium in there, but in their own material, in that material system, would be more robust and resistant to radiation damage in terms of the dark current increasing. That it would not increase, because we've seen that on pin photodiode arrays in MERCAT Telluride that are already used on Hubble Space Telescope, for example.
Okay, I think we have another question from a graduate student here, Kim Culp.
Hello. My question has to do with alternatives to the linear mode and guided mode APDs that you were talking about. And I was wondering if you'd ever investigated using EMCCDs for your array-based applications.
Yeah, that's a great question, and yeah, thank you. And yeah, we have when you can time integrate. So here I was trying to get nanosecond time resolution, or even sub-nanosecond. So we even talk about, actually, we love 50 picosecond time resolution. But some of the application where you can integrate longer, say the trace gas detection or even wind LiDAR, you can definitely use silicon CCD arrays in a fast clocking mode, and you can probably get some sub-microsecond timing out of those. It's going to be hard to get down to a nanosecond, or especially sub-nanosecond in that CCD array, as far as I know. But we'd certainly be open to it, and they have been used in ground-based. I know on the wind LiDAR for sure, because when you're looking at the atmosphere, again, you don't need the height resolution that's required for the ground topography measurements, and especially when we're measuring ice melting. So when we're looking at ice melting, we want to get down to definitely to 1 centimeter or even sub-centimeter resolution, and average. I mean, of course, all that's time average, but as you know from the Earth here, many people now are interested in tracking the polar ice sheet, the melting of the polar ice sheets, and not just the polar ice sheet, but definitely the polar ice sheets and ice around the world, down to that centimeter or sub-centimeter level. And so we need that kind of height resolution. And also, as I talked about before, for measuring the tree canopy height, the height of a tree, then you need to measure the ground surface. And you definitely want to know the topography of the ground to a few centimeters to measure the tree height canopy. Did that answer your question?
I think so. Thanks very much. Are there any questions out in internet land? It looks like there aren't any other questions typed in the chat window. Okay. If not, then let's thank Mike again.
Okay, thank you all. I really appreciate this opportunity, and it was fun to do the virtual work.